So this is just to continue on our work and energy right here. This is just the third lecture on it. And you remember what we said before was that the total work, when you added it all up, it just equaled the change in kinetic, where this is the definition of kinetic energy, 1/2 mv squared right here. So when we said we had all these works, that's the total work right here. We said we could get rid of these two right here. And this one we said was a conservative force, and we can write it as minus a change in potential, where potential was mgh. Remember, change always means final minus the initial. Now, you noticed right here, anytime you have friction, energy leaves the system right here. So this one, energy is leaving. Here, energy does not leave the system. Any conservative force, it stays right here. It goes into potential energy. But here, you hit the brakes on your car, you're losing that due to heat right there. The work due to P right here, that's your hand force. Well, you could be helping it or you could be fighting it right here. So this one, energy either enters or leaves the system depending on what you're doing. So these are the two ways that energy can get in and out of a system right here. Okay, so now let's just assume, let's work out some problems where these aren't there. No energy can get in or out. There's no friction and you're not touching it right there. If that's the case, then these two are both zero, and I can take this term and put it on the other side and make it positive, and we got the change in kinetic plus the change in potential due to gravity equals zero. Or if we write out the change as the final minus the initial, and this as the final minus the initial, and put all the initials on this side, K naught would be positive and U gravity naught would be the positive. Now we got the initial gravitational plus the initial kinetic is the final gravitational plus the final kinetic. The total energy of the system stays the same. It can't leave right here. So as long as we know all the heights and the speeds at one spot, we know all the heights and the speeds at another spot. Makes life a lot easier right here. So let's look at examples of this case where we don't have any friction or we don't using our hands in there. Well, let's just look at a projectile right here. We throw a projectile off a cliff. You've done that plenty of times. We're looking at it after it left our hand. So there's no hand force right here. So you'll notice right here, the kinetic plus the potential here should equal the kinetic plus the potential there. Now I can call H equals 0 for my potential equal to 0. Any spot I want, I always like to call the lowest location 0. If I called the location way up there 0, then these would be negative numbers for heights, right here. Remember, we have to call positive upward when we're using our potential energy. So right here, it's got some potential. Well, it has a height, H, so it's got mgh, plus it's moving. Looking at after I left my hand, 1/2 mv naught squared. So it's got those two energies. When it got down to here, it didn't have any potential. He said H is 0, but he has a final velocity right there. Well, these two are the same right here. Just set those two equal, since energy can't come in or out. Set this equal to that. Cancel the multiply by 2. Cancel the m's and take the square root, and this is exactly what you had from, what would it be, that chapter 3 right there. But you'll notice, didn't have to write out coordinate systems, don't have to break vectors up into their components. Everything here are scalars, makes life a lot easier. So you can see just working out this. Now if I wanted to find the time and stuff, well, there's no time in these equations, so you're going to have to go back to your constant acceleration. But at least velocity versus position, this is much easier using energy. If we look at this case right here, now we've got two blocks right here. We've got a 3m and an m, and it's held like this, and now all of a sudden we pull our hands away, and this one's heavier, so it's going to go down, this one's going to go up, and we'll take a snapshot of it right there. So we'll say it starts from rest here, and then we let it go, and now as it gets all the way up to here, we'll take a snapshot of it just as it was going by right here. And now let's apply energy to this. Let's say we're given the height, how high up this one, well, how much this one dropped. which is exactly the same amount that this one went up right here because our ropes don't stretch. Find the speed of the two objects. They're going to be the same because they're tied together. So we look at the energy when they're like this and here, and we look at the energy when they're in the green over here, and we set those two equal because energy can't get in or out of the system. So right here, since I'm going to call, now you notice for the height equals 0, I can put each block his own height equals 0. So this block went from here to here, so I'm going to call this height 0. This one went from here up to here, so I'm going to call that height 0. They don't have to be this, they don't have to share even the same h equals 0. So this block, we're looking at it in the black first right here. This block has no kinetic. They start from rest, but it has potential. It's got 3mgh. So there's the 3mgh. This block has got no kinetic and no potential, so it's 0. So the total of the two blocks is 3mgh. Now, when they're up in this green configuration, this guy right here, where are we? Down here. This one right here has no, it only has kinetic energy. And so this block went up, so this block gained some potential right here. So he's got some potential, mgh. He's also got some speed, so he's got some kinetic, 1/2 mv squared. And then this one also has some kinetic, 1/2 3mv squared. So you notice what happened here is all of this potential energy, when he dropped, he gave it up. He gave it up to lifting this and giving these two speeds. And so we're just keeping track of the energies right here. That's all we did. Okay, so setting those equal, the initial energy, 3mgh, equal to all the final energies. And then I can combine the mgh's together, and we can solve for the velocity right there. Velocity is just the square root of gh. You notice if we were going to do this with try to find this from earlier work, we would have had to look at the forces on this, take the sum of the forces here, sum of the forces, list them all out, solve for the acceleration, then plug it into the constant acceleration equation to get that. You might even try that, doing it just to make sure you get the same answer right here. Matter of fact, I did it right here. I said, let's just come over here and let's just look at the forces. Here I have 3mg and a t, and I looked at, in this one over here, I have a t and an mg, and I'm going to call this way positive and that way positive because I'm looking at forces right here. And so we said 3mg for this one minus t equals 3ma. This one, we had t minus mg equals ma. And now if I just add these two equations together, the t's drop out. And we just get 3mg minus mg equals 4ma. And then put the mg's together, cancel out the m's, and you get a equals 1/2 g. And then we know this is a constant, so we plug in our constant acceleration equations. And I'm just going to do it for this guy. I don't care about that one. We'll just look at it for this one right here. V squared equals V naught squared plus 2ax minus x sub naught. It started from rest. 2a is 1/2 g. So the 2's drop out, and you get v equals the square root of gh. It's exactly what we got before. So again, we have two ways of working out all these problems, but this way is going to be a lot easier, especially when we get even more complicated problems right here. Just look at the energy before and the energy afterwards. You can do that as long as there's no work due to friction and you're not adding or taking it away with your hand. Okay, so we'll just continue on.